Hi everyone, so welcome back to our channel. We are going to start with the third video of LLM Mastery, and this video is going to be one of the most important things which we are going to discuss, and that we are going to discuss about the full transformer model. Each and everything in much detail I will explain you in this video. We'll start with the discussing about the LLM transformer model. We'll start with the something related to the input embedding that is there in the part of once we have the input data, how we are just going to go with the position encoding. Then we will have a multi-head attention mechanism. We will just discuss about the encoder concept, what we have, the whatever the components we have in the encoder. And then after slowly we will move with the multi-head attention. We will understand the mechanism behind the multi-head attention. We'll go with the addition and normalization concept, and once we have just completed this thing, we will also read about the feed forward neural network that is there in the transformer model as well. And then once it is the encoder part is completed, we are going to go with the decoder components. In the decoder components, most of the component is similar to the encoder, only there is one of the more key things which has been included in the decoder that we will discuss again in this video, that is a marks multi-head attention mechanism. And we are going to discuss this thing in much details. So that's why I have just made this specific video, that is a transformer video in much detail, so that you can just see and visualize that how the transformer model has been started, from where it has been there, and so many of type of the things are there in the market nowadays. And most of the GPT architecture, BERT architecture, they use the concept of the transformer there. And finally we can just wind up by this by discussing about the what's going to be the linear and the softmax, and what is going to be the output things. So let's get started. The first thing about the transformer model. So here we are going to see about the diagram. The left hand side you are able to see, that is totally an encoder model, and the right hand side is basically a decoder model. So what's the encoder and decoder? Because whenever you are studying about the transformer model, I hope so you have really clear concept of RNN and LSTM, because they were really the first sequential model of the deep learning for the NLP tasks. And slowly the attention mechanism has came, and then now the transfer model has been taken place, and it has been giving a really a good type of accuracy. Because the way we are using in RNN and LSTM, it was totally a sequential type of data training, but in the transformer we use a parallel type of data training. And again, this thing again we have discussed little bit about the transformer and history and evaluation of LLM model in the previous video. So let's get started with the this video, that we are just going to go with the definition first. So basically the transformer model is going to consist of an encoder and the decoder. So encoder we already discussed, this part is basically encoder side, and this is part is basically a decoder side, and both build with the layers of the multi-head attention normalization and the feed forward neural network. And again, this thing I'm going to break down in the parts, like we will go in the really depth with the input embedding, position encoding, multi-head attention, and finally we'll go with the add and norm and the feed forward neural network for the encoder side. So encoder process the input sequence while the decoder generate the output sequence. Again, once you are able to understand this concept, because whatever the input data you are feeding, that will be in the encoder side, and whatever the output data is generating, that will be in there in the decoder side. And the final output is produced by the passing the decoder output through a linear layer, and that we call as a softmax to obtain the probability. I hope so you have used so much of time about the softmax whenever you are going to do some multi classification problem. So let's get started with the first thing, that is the input embedding. So input embedding is basically what the purpose of this. So whatever the text data you are going to provide to the data encoder side, that's convert the input tokens in, that is whatever the words you will have, into a dense vector. Because whatever the sentence you are just going to provide, it is going to break into a words that we call as a word tokenizer. And then after finally it is going to have a provide you the dense vector for the every words. Because the how we are going to do this is basically each token is mapped with the high dimension vector that capture the semantic information in that. Because whatever the text data you are going to provide, you need to convert into a numeric form. Either previously we were just doing with the one hot encoding, but nowadays there are so much of method has been came. We use a word to vec model, it is going to be give you the best result. We use a elmo model, and different type of word to vec tokenizer is there. So the first step is basically tokenization. We just do the first tokenization. It's like we are just splitting our text data into a words, and then words is a word or whatever the character we have, we can map with the words also as well as the character. So most often we just do with the words. To we need to give the meaningful meaning of that specific word. And then after we are going to apply embedding lockup. So each token is going to map to their dense vector using a embedding matrix. You can go with the any word to vec model. I am going to use here normal word to vec model. Suppose I have a sentence and the sentence is I love AI. Correct? I love AI and I'm using a dense vector of 3. So I love AI. We are going to provide the vector. This is the example normal I'm going to explain you. So I vector stand for the 0 0.1, 0 0.2, 0 0.3, and the love vector is going to be similar type 0 0.4 and so on, and AI going to be so on and so on. So basically you are going to represent I love and AI with a vector, and each vector is going to represent by the in the list you are providing how many dense vector you have. So for now I'm just providing only 3, and total words also we have 3. Now this is what a input embedding basically means, that you are just converting your sentence into a word tokenizer, and every word tokenizer you are converting into a vector forms. So once you are able to do in this thing in the first transformer, then you are moving with the positional encoding, and because you are going to add the input embedding with the positional encoding. So why we are using position encoding in the transformer? Again, this might be a question. We have used a RNN, we have used a LSTM, but there is no concept of the positional encoding, because they are able to match the, and they have that kind of tokens. Like the first time stem they are going to provide some input, the second time stem they are going to provide some input, so they are able to have some positional encoding there itself. But in the transfer you don't have anything sequential wise, because whatever you are just doing in the LSTM and RNN is going to be a sequential wise. But how whenever you are opting for the parallel, you are going with the position encoding. And this position encoding is basically, again I will give you in much details, this is what I am just talking about. Either it is for the encoder, either it is for the decoder, it is going to be the same. So the what's the purpose of this position encoding? That's going to add information about the position of each token in your sequence, because whenever you are providing doing an input embedding, you lost the sequence. You have the vector, meaning that I represent with this vector, love represent with this vector, AI represent with this vector, but you don't have the things like whether this I love AI is going to be in the sequence or not. So that for that reason you are going to use the positional encoding. And how we are going to use, they use the concept of using a sine and cosine functionality to create a unique position vector for the each token where it is added into input embedding. Again, the sine and cosine similarities basically means that whatever the input embedding you will have, you will take in the sine and cosine terms, and then after it is easy to give the sequence type. Whatever the value you will have, you are going to find, you are going to pass into sine and cosine value, and it is going to give you some values like the position encoding of the first vector. I'm just going to say something like 0 0.1, you are going to something get like 0 1 0, and for position 1 you are getting as 0 0.8 0 0.5 0 0.8, and position 2 you are getting as 0 0.8 0 0.4 and 0 0.9. It basically means that for the I vector you have three vector, for the I you will have a three dense vector representation, and then three whatever the inputs you will have, you are going to add with the every position encoding, like 0 0.1 plus 0, 0 0.2 plus 1, 0 0.3 plus 0. So 0 0.1, 0 0.2 and 0 0.3 is basically your the input embedding vector, plus you are just doing the positional encoding. So you are going to get a positional encoding of I vector as 0 1 0, because total vector you will have only 3. Similar, you are getting a position for the love vector, you are getting a position like 0 0.8 0 0.5 0 0.8. Now you are going to concatenate this 0 0.4 plus 0 0.8, like 0 0.4 plus 0 0.8, similar 0 0.5 plus 0 0.5, something you are going to do like this, and you will get a position embedding that we call as a positional encoding. So I hope so it's really the basic you will able to clearly understand with this example. So once you are able to done with the positional encoding, you are ready, you are just saying you are ready for the model to pass to the first thing that we call is multi-hit attention. Because whenever you have a position encoding, you know what is the sequence of your sentence. I came before the love, and love came before the I. You have the sequence, you have the word embedding. Then we are going with the this is the what encoder concept it is there. This is the what we call as an encoder components. So in that encoder components you will find something like multi-head attention mechanism. Then on top of that you will use an add a norm, and add a norm basically means that we will use the feature of skip connection, and then we will do the layer normalization. This again we are going to discuss in the much detail. And then after we will have a feed forward neural network, and then again we are using a add and norm. So what is the purpose of basically using this type of components? It's like each encoder layers contains this two sub type of layer. The one we call as a multi-hit attention, another we call as feed forward neural network, and both are followed by the addition and normalization of the step, whatever the layer normalization we are just going to do. And again we are going to again go with the details of multi-hit attention. First of all, we'll understand what the concept of multi-hit attention. So whenever we are going to go with the multi-head self-attention mechanism, I hope so it will be really easy for you. So what purpose we are just doing? So we are allowing our model to focus on different part of the input sequentially and simultaneously. What does it basically meaning of this? Because see, the thing is that whatever the if you know the concept of attention, self-attention, it's like you are just going to create a group of self-attention, and that is called as a one multi-head attention. So you are going to see about the shadow. So this is the one fully multi-head attention. Second, you will find the second multi-head attention. So in the transformer model you will you might have give the input that I need a 8 total multi-head attention. So basically you are going to see that this is going to concatenate and into single vector, and then after you are passing to a linear that we call a feed forward neural network. So basically means that whatever the values, the keys and the queries you will have, you are going to go with the you are going to go with the dot product between the values and the key. And then after you once you will have, you are going to do the scale product, whatever the output you are going to get with this. So that every word is going to focus on different type of the words. Like I love AI, I will multiply with itself. I will multiply with scale dot product with love, I will do the scale product with AI to find the semantic similarities, to find the sequence, basically to find something there is there related with every words whatever we are going to say about this all thing. Now the how we are just doing this whole thing, we use a multi-head attention head. Basically head whenever we are just talking about, it's like you will have a multi-head attention head, and that's going to combine and process the process for the basically concatenate you are doing, and then you are going to give some output into a dense vector. So first of all what we will do, we are going to provide the input embedding, whatever the input embedding we are just getting from this position encoding and this whole thing. Once you will have, you are going to get into linear projection of sorry, the keys, queries and the value. So suppose you will have these vectors 0 0.1 1.2 and 0.3 for the I vector. Then you are going to pass with the key value, keys and the queries. The same vector you are going to multiply to find the similarities between the words. And if the words will have the similar type of word, they will have the more similarity, cosine similarity you will have. And then after on top of that, whatever the value you are getting, you again we are going to go with the you are going to multiply with the say again the scale dot product, and you are going to get some output. Again I am not going to be really going with the mathematic formula for now. I am going to say you explain you about what exact we are just doing in the transformer model. So I hope so you really understand about the multi-head attention mechanism. It's like you are just combining the multiple number of self attention mechanism into a grouping into one, so that every self attention mechanisms will focus on different variety of the things to find the similarities between the words. Because every self attention mechanism will focus on different type of similarities. It first might be go with the something related to the a positive type, some might go with the negative type, some might go with the to find the similarity. That's what we are just going to group on and just concatenate with a single vector and then passing to the linear layer. So it's not compulsory that you are going to pass only one multi-head attention mechanism. There might be a multiple head attention mechanism. There might be something 8, I need 8 total multi-head, and inside the 8 you will have that I need 64 total number of self attention mechanism. So I hope so you are really clear with this concept. Next we are going to move with the addition and normalization. this is going to be really the one of the key factor whenever you are training your model and whenever you are updating your model during the back propagation, because during the back propagation you are updating your weights. So what the step we are just going to take in that is like you are just going with the residual connection, and the second you are going with the layer normalization. So residual connection, I hope so you study about the ResNet there, how we are just using a skip connection to go more deeper in the network, so to avoid the vanishing gradient problem. Similar type of concept we are using now here. So what we are just doing, the first of all the residual connection, it's like whatever the you are going to get the input from the multi-head attention, as also whatever the previous sublayer output you are having, then you are going to add and then perform a layer normalization on that. So it's like the input to add a addition and normalization step is added to the output of the previous sublayer, that we call as a multi-head attention. You are getting some output from this, and again you are going to get output directly. You are just taking this output that we call as a previous self output into addition and normalization layer. So this addition help in mitigation the vanishing gradient problem, which already I discussed during the back propagation while your flow of your training and updating your way, so that your models will not be go with the vanishing gradient problem. And once you are able to add this thing, you are going with the layer normalization. So layer normalization is basically x minus mu by, you can just x minus mean by standard deviation into scaling into whatever the factor you are just having. So this is the layer normalization. I hope so you have, you know, the concept of normalization you might use in the CNN, ANN, RNN much of the time to normalize your input data into a similar type of form, so that after adding this residual connection, the result is passes through a layer normalization step. And the second we are going to say that layer normalization that normalize the summarized output by subtracting the mean, that is whatever the mean we have, and dividing with the standard deviation, whatever the standard deviation we are getting for that specific after the concatenating the previous sublayer and the current sublayer in the layer, and followed by the learning, scaling, and the shifting. And this is basically gamma, we call it that they are the learnable parameter during your training time. So gamma is basically, you can just say it's like you will have something all the scaling factor you will have, and the beta is basically the shifting factor, so that you will have regular time, you will have the scaling of your input data, and while during the back propagation while updating your weight, your model will not suffer from the vanishing gradient problem. So I hope so you have cleared the concept of the addition and normalization. Now we are going to go with the concept of the feed forward neural network. This is going to be the last step in the encoder section, because in this is normal, if you know the concept of ANN or neural network or fully connected network, it's like the same thing. You want to apply a non-linear transformation in your data. So whatever the model you have, you want to make that model as a non-linear model, and how you can just introduce that one to learn to linear transformation with the ReLU activation function in between them. It's like you are just using a ReLU activation function to introduce a non-linearity concept in your the model, and then after your model will able to learn the different type of complex pattern inside your neural network. Once you are just training any feed forward neural network, you will find something pattern inside that, and that's from that pattern they are learning and making the model more complex and the complex to find the pattern. So I hope so you understand each and everything about the first of all about the encoder section, because this encoder section you will have all the thing about the multi-head attention. We just talk about the addition and normalization, we talk about the feed forward network, and then again on top of that you are again applying addition and normalization with the concept of skipping connection, that we call as a residual connection. Now we are moving with the decoder section. In the decoder section we have the components that we call as a the marks multi-head self attention. Everything is going to be the same. You have an output embedding, you are going to do the same type of embedding, you are going to add the same type of the position encoding. After that you are going to apply a marks multi-head attention. I will go in much. So Mark's multi-head self-attention mechanism is the key concept in the decoder section, which we are going to check in the much details in this video. I hope so you have really clear concept of the encoder section, but in the decoder section you are going to add up one new things that we call as a Mark's multi-head attention, and the second thing is basically you will have some linear layer, and top of that you are going to use a softmax to to predict the output probabilities, and we are going to check in details in this upcoming slides. So let's get started with the first things that we call as a marks multi-head self-attention. So what the purpose of basically is that, so we are just going to prevent the model for attending the future tokens in the sequence, so that we can ensure the predicting are based only on the past and the current tokens. So it basically means that we are just avoiding the leakage. We are not allowing our model to see the future, whatever the word is there, based on whatever the previous they have learned and whatever the current they are just going to learn. Based on that, you are going to, the model is going to predict the future words. They are not allowing to access the what is the future word is there, and based on the future word you are going to learn that one. So that is no, there is no such leakage. So basically we are just going to see how we are just doing. It is the same as it is of the multi-head attention mechanism, which we have already discussed in the encoder section. Only the thing is that we are introducing one new thing that we call it, we are just marking the information leakage. The future word whatever is there, we are not providing the information in the decoder section where we have the marks multi-head attention. So it's like the same step we are just doing in the decoder also. We have a input embedding, we are just converting into a whatever the linear projection. We have a query key and the values. Then after we are performing a scale dot product, the way we have the discuss about the n number of self attention mechanism, and each self attention will have going to focus on different perspective of your text data. It might be a semantic relationship they are going to find in your the text data, and then after they are going to again concatenating the head and giving you final linear projection. There is nothing different between the encoder section and the decoder section that we call as a marks multi-head attention, except we are not allowing our model that is a marks, we are keeping a marks for the future words, so that the model can learn from the current words and then the previous whatever they have predicted. Next we are going to go with the multi-head attention that we call as a encoder and decoder attention mechanism, because this is also one of the key component in the decoder section, because you are going to take the input from the encoder as well, and as well as the decoder of the previous marks multi-head attention. So what the purpose is that you are just going to allow the decoder to focus on relevant parts of the encoder outputs, because whatever the output we have in during the feed forward neural network, we are going to pass the input to this we call as a multi-head attention. Here it takes two input. The one we call one we say that it takes the input from the encoder section, another it takes the input from the marks multi-head attention after performing some normalization, layer normalization. So how we are just doing, we are just going to attend this encoder output sequence to gather the context of your data. The first thing is basically the input from the previous decoder layer. So the previous decoder layer, we are just talking about the marks multi-head attention. So what is going to be the input in this, we are going to discuss here. The first input is going to be the previous decoder layer, and that is we call as a marks multi-head attention. So the input in this sub layer is going to be the previous sub layer. Whatever the decoder is going to predict is going to marks multi self attention or another multi-head attention sub layer, whatever the layers you will have. The second thing, the input you are just taking from the encoder section, that we call as a encoded representation from the encoder servers, serve as a input for the keys and the values. So whenever you will check about the full image about the encoder and decoder, you are going to see that this whatever the output you are getting, final output you are getting from the encoder section, it is fitted into decoder section of this, especially after the marks multi-head attention mechanism, so that it is going to take two input. The one is the marks, another is the real whatever the encoder is going to give you the output. So yeah, so in this basically what we are just going to perform, you will have something we call as a linear projection for the queries, keys and the value, because the decoder input is a linear projection into a queries. Whatever the queries you will have, you are going to you will have with the representation with the queue, and then from the encoder section you are going to take the keys and the value. Again you will do the some dot product between the keys and the queries. So what if the decoder and the encoder, because whatever the, suppose you have something like I love AI, and then after you are going to translate into another language. For the encoder you are going to have a representation of I love AI. For the decoder, whatever the translation you will have, you will again have something word embedding, and the after passing to the multi-head attention you will have some encoding vector, and then after you are going to perform the scale dot product between the encoder output that we call as a key and the decoder output decoder output after the marks multi-head attention we call as a queries, that you are going to perform a scale dot product. And then after you will have a final layer that we call as a linear and the softmax activation function, that after applying addition and normalization, it is the same concept what we have just done in the encoder section. We perform a layer normalization so that we avoid the vanishing gradient problem. So after once we are just done with this, we are just using a linear layer. And linear layer is basically, it is going to transform the decoder output to a desired output size, whatever the size you are going to expect. Because in the whenever you are just talking about the text data, you need to provide you the fixed vocab size, and that is what we are just going to perform in the linear layer. And it's basically applied in the linear transformation. And the softmax, already you know about the activation function, is going to convert the linear output into probability. It's going to, if you have multiple we already use in much of the things, like even for the image classification, whenever you have multiple image classification, you are going to take that softmax as a probability terms to predict what is going to be your the final output based on the higher probability. So it is going to convert the linear output into probabilities. And how we are just going to apply it, so we are going to apply a softmax activation function to generate a probability distribution over a vocabulary for each token. And whatever the tokens you are going to get, you are going to get the probability of this, and the output probability is going to represent the final prediction of each token in the output sequence. What is going to be the output, what is going to be the translation of your the one from one language to another language, what is the semantic, whatever the application you are developing, whatever the task you are performing with this transformer, it is able to do all. And then after how we are just doing, we are just the model selected, whatever the model selected, we have the token, and whichever has the highest probability in each position to generate the final output sequence. So I hope so it was really the clear concept about the encoder and decoder section. And in the decoder section, we already cover much of the things in the decoder section. And in the encoder section also we have just completed all the things. I hope so you have really clear concept about the encoder as well as about the decoder. And we have went with the each and every step, what understanding about the input embedding, position encoding, multi-head attention, self attention, and then after addition and normalization, and what the decoder is going to take from the previous input of the that is the current input, current output from the encoder, as well as the previous input from the multi-head marks attention mechanism. And we call as a marks basically that we don't want our model to see about the what the future word is there based on the previous word whatever they have learned, and the current word they are going to predict the features, future words. And then after we are going to do the cell again the scaling, that we call as a scale dot product between the this input that we call as the keys, and then after queries of this. And then finally we just fit it into self attention mechanism that we call as a feed forward network. And then finally we are applying a addition normalization on that, and we are passing into linear layer so that we can have the fixed size of vocabulary whatever we are just training. And top of that we are applying a softmax activation function, that what the exact sentence which has the higher probability is going to give you the outputs. I hope so you have really clear concept with the transformers. In the next video again we are going to check about the some new model of the transformer, a variant of the BERT model, T5 model, GPT architecture, and various type of architecture. I hope so you like this video. Thank you so much.